Hello all and welcome to this video. Today we are going to discuss few commands that we use in BGP like neighbor command, update source loopback and ebgp multihop command. We know where we use them and when do we use them. But today my agenda is to discuss why we use them and what is the importance and significance of these commands. So let's get into it. So the first command, that is the neighbor command. We all know that when we are configuring a BGP neighborship between two routers. For example, in here, the two routers are R1 and R2. The network between them is 12.0.0.0/8 network. So dot 1 is on R1, dot 2 is on R2. R2 belongs to AS number 200 and R1 belongs to AS number 100. So you can see that under R1, I have written the common BGP command, that is router BGP 100, and neighbor 12.0.0.2 remote AS 200. So 12.0.0.2 is the interface IP of R2, and similarly on R2 with the neighbor command 12.0.0.1 remote AS 100. 12.0.0.1 is the interface IP of R1. So I would like to tell you the why behind the neighbor command. What is the significance of the IP address that we have mentioned? So what happens is that when we give a neighbor command during a BGP configuration, the neighbor command on R1 and the neighbor command on R2 both have different rules. Meaning that when on R1 we write neighbor 12.0.0.2, so what happens is that R1 starts to create a TCP session with the destination IP address. So here the destination IP address, as we have mentioned it with the neighbor command, is 12.0.0.2, right? So the next thing is that it now needs the source IP. What would be the source IP? 12.0.0.1, right? 12.0.0.1. But just looking at the diagram, we cannot assume the source IP should be 12.0.0.1. Let's think of how R1 processes the source IP, or how R1 finds out the source IP, right? When we give the IP address as 12.0.0.2, R1 first checks in its routing table to which network does 12.0.0/8 belongs to. And in its routing table, it will be associated with an exit interface. And in this case, I'm assuming the exit interface is fast Ethernet 0/0. And this exit interface would obviously will have an IP address. And this IP address becomes the source IP. I repeat, when we give the destination address in the neighbor command, R1 checks to which network does this IP address belongs to. In R1's routing table, it would see this IP address belongs to 12.0.0/8 network, and 12.0.0.0/8 would be directly connected to an interface. And in this example, I'm assuming that interface is fast Ethernet 0/0. And this fast Ethernet 0/0 would be the exit interface, right? And this exit interface would obviously have a source IP address, and this source IP address will be mentioned in the TCP session. So it is not necessary that based on the diagram, R1 chooses the source IP as .1. If this was 4.4 or .5 or .6, the R1 will choose that particular IP address based on the steps that we saw earlier. So here what happens, source IP is chosen as 12.0.0.1, and R1 creates a TCP session with the source IP and the destination IP that I have mentioned here, right? Now, as I was saying, on R2 the neighbor command has a different role. So what happens is that when I give a neighbor command 12.0.0.1, so basically R2 is expecting a TCP session from the source whose IP address is 12.0.0.1. Similarly, when I do a neighbor command on R2, R2 creates a TCP session, and in the TCP session with this command line, the destination IP will be 12.0.0.1. So the source IP, it again checks in its routing table. In the routing table, it will check that 12.0.0.0 belongs to or is associated or is connected to which exit interface. That exit interface, again, I'm assuming it is fast Ethernet 0/0. This exit interface will obviously have an IP address. That IP address will become the source IP, right? So in our example, that source IP is 12.0.0.2. And similarly, the neighbor command on R1, that is neighbor 12.0.0.2, is basically expecting a TCP session from the neighbor with the source IP 12.0.0.2. And this is why the neighbor command is very specific. So let us assume that the IP address that I create here on R1's this interface fast Ethernet 0/0 is not .1, is, let's assume it is .4, but I am not changing the neighbor command. Okay, I'm keeping the neighbor command as 12.0.0.2. So what happens? R1 creates a TCP session with the destination IP as 12.0.0.2, the source IP, right? Source IP, it would check in its routing table that 12.0.0.0 is connected to the exit interface fast Ethernet 0/0, and this fast Ethernet 0/0 has an IP address of 12.0.0.4. So the source IP here is 12.0.0.4, which basically R2 is not expecting. R2 is expecting a TCP session with the neighbor whose source IP starts with 12.0.0.1, and hence the TCP connection or the BGP TCP connection between R1 and R2 will fail. So the neighbor command is that important in BGP sessions. So moving on to the next command, update source loopback. In this diagram, R1 and R2 both are connected through one physical link. In our previous discussion, what we saw how a TCP connection is formed using the neighbor command. Now let us assume that the BGP peering is up, the TCP connection between R1 and R2 is going well. So for example, let us assume that the connectivity between R1 and R2, this link goes down. There is some problem with the physical connectivity. So what would happen is that when there is no physical connectivity, the BGP TCP session between R1 and R2 will also fail. The TCP session will not work. So that is why we create the neighborship between R1 and R2 or two BGP peers using their loopback address, because loopback address is always up. So on R1, let us say that I give the command neighbor 2.2.2.2 remote AS 200, and similarly on R1 I give the command neighbor 1.1.1.1 remote AS 100. Okay, and let me remove this command. So now let us see what would happen in continuation to our previous discussion. When we configure this command on R1, the destination IP is 2.2.2.2 and the source IP. Now let's check what the source IP would be. Here I'm considering that R1 knows how to reach 2.2.2.2, and similarly R2 knows how to reach 1.1.1.1. It can be through a static routing or a dynamic routing. So R1 would check in its routing table that 2.2.2.2 would belong to 2.0.0.0/8 network, and the exit interface would be fast Ethernet 0/0, and on that fast Ethernet 0/0 the IP address is 12.0.0.1. So the source IP here would be 12.0.0.1. But what is R2 expecting the TCP connection from? R2 is basically expecting a TCP connection whose source IP is 1.1.1.1. So basically again your TCP connection will fail. Similarly on R2, when we give this command neighbor 1.1.1.1, the destination IP becomes 1.1.1.1, the source IP, okay, with the same steps that we saw earlier, the source IP would be 12.0.0.2. But R1 is expecting a TCP connection whose source IP is 2.2.2.2. So again, here TCP connection will fail. So when your TCP connection fails and your IP addresses or the source IP in the neighbor command is different, your TCP connection will fail. And hence, we give the command here, we use the command neighbor 2.2.2.2 update source loopback, right? This is the same command we gave on R2 as well. Neighbor 1.1.1.1 update source loopback. This is the reason we give this command, so that when R1 is sending or creating a TCP session, the destination IP is 2.2.2.2 and the source IP, because we have given the command to update the source as the loopback address, and on R1 the loopback address is 1.1.1.1, and which by the way R2 is also expecting the same. Similarly, on R2, when we give this command, the destination IP becomes 1.1.1.1 and the source IP is 2.2.2.2, which basically R1 is also expecting from the TCP connection that is being sent or being received from R2. Now moving on to the next command, important command, ebgp-multihop. Right. So here if you see, I have three routers R1, R2 and R3 and they belong to AS number 100, 200 and 300 respectively. You can see the loopback addresses on R1 and R3 and the IP addresses on each of them. So we all know that BGP peering or BGP neighborship can be done with direct subnets and indirect subnets. So here I am basically considering that the two routers are not directly connected. So in this case, R1 and R3 are not directly connected, but still we can have a BGP connectivity, eBGP connectivity between them. On R1, when I do a neighbor command 23.0.0.3 remote AS300, what R1 does is the destination IP would become 23.0.0.3, the source IP, provided we are using the command update source loopback, right? The source IP would become 1.1.1.1. And what happens is that R1, first, what it does, it checks if 23.0.0.3 is directly connected with it or not. So it would see that 23.0.0.3 belongs to a network 23.0.0.0/8, which is connected, or to reach the network, it needs to use the exit interface fast Ethernet 0/0. So what happens is that R1 automatically knows that this particular network is not directly connected to it. So R1 will not send, will basically not create a TCP session in the first place. In order to avoid this, what we usually do is that by default on your eBGP, there is a feature called as directly connected check, direct connectivity check, which basically tells the router to check if the neighbor that you are trying to connect or that you're trying to have a BGP peering with is directly connected or not. So if we disable this feature, R1 would ignore if 23.0.0/8 network is directly connected or not and will create a TCP session. Now, considering the fact that we have disabled this and the TCP session has formed. So what would happen is that when the TCP session is formed, the TCP message reaches R2, but then R2 sees that the TCP connection that R1 is trying to create is with 23.0.0.3, and on R2's routing table 23.0.0.3 is not directly connected to it. And in eBGP connectivity, we all know that the TTL value is 1. Okay, so obviously when R2 sees the destination IP as 23.0.0.3, it knows that it needs to forward this BGP connectivity to the next hop, that is R3. But then it needs to decrease this TTL value. So it decreases this TTL value to 0, right? And then what happens? R1 will never be able to create a TCP connection with R3. Similarly, even if R3 is trying to create a neighborship with R1, it cannot happen because the TTL value for eBGP connectivity is 1, which when reaches R2, R2 will decrease it to 0 and will never be able to forward this to R1. And that is why we use, when your destination network is multiple hops away, that is why we use the multi-hop command, neighbor 23.0.0.3 ebgp multi-hop, and we give the number of hops that it is away from. So in this example, I'm giving the command 2. And similarly, we do the same command, or we configure the same command on R3 as well. Now, when we do this command, what happens is that when R1 sends the BGP connectivity or TCP connection to R3, R2 with a TTL value of 2 here, by default, the TTL value in eBGP connectivity is 1. But in this case, since we change the value to 2, the TTL value becomes 2. And when R1 sends this TCP connectivity, R2 decreases that value to 1 and then again forwards it to 3. Similarly, on 3, when it sends this BGP connectivity message, R2 decreases the value from 2 to 1 and forwards this message to R1. And hence, the two routers R1 and R2, though they are not directly connected with each other, can still create a TCP session between them. I hope this short video on BGP commands, especially the neighbor command, the ebgp multi-hop command, and the update source loopback command, these three commands were important, and I hope you understood the reason behind their significance. Please like, share, and subscribe this video, and have a great day. Thank you.